The authors of the paper are Stefan Rankin, Bing Tan, Barbara Knudsen, and Hans Lechner. The title of the talk is Surfactant and Plating of Ordered Nanopore Silica, which is a very interesting and very exciting area. So let's hear Stephen Rankin giving his results.
Thank you very much. Thank you for the introduction, and thanks to everyone, well, and to Yushi Graham for inviting me to talk here and letting me know about this meeting. So what I'm going to talk about today, this is just kind of a preview of the kind of materials that I'm talking about, are ordered porous materials that, you can see these are the pores that I'll be talking about eventually. They're about 2 nanometer, or well, closer to 3 nanometer pores. But just generally, to give you an idea of what, I'm just kind of introducing myself, I guess, since I haven't been involved in the tri-state catalysis club before.
Excuse me.
Yes, I don't know. Maybe. So, can you hear better now?
Yeah.
Okay. So the types of materials that I'm interested in, now I'm going to warn you that I don't actually work in catalysis. I'm just trying to make porous materials, which should have applications as catalyst supports. But I am going to try to give you a little bit of an overview of the field, and other people are making catalysts out of this type of material. But the kinds of materials that I'm interested in include porous materials and organically modified ceramics. So it always has something to do with silica and siloxane networks. So for example, the kinds of materials are zeolites, these surfactant templated molecular sieves, and this is an example of a particle, and this is what I'll be talking about today. But we're also interested in materials like aerogels that are just very low density, high surface area materials, and organically modified ceramics. So the surfactant templated materials, let me move over here, that I'm going to be talking about were first discovered, I mean, actually, supposedly some were made earlier, but people really realized what they had in around 1992. And this surfactant templating was really discovered kind of by analogy to making zeolites. So a lot of synthetic zeolite processes are hydrothermal. So you mix together an organic ammonium cation where all the R groups can be, you could choose them independently depending on what kind of zeolite you want to make. And so there are a lot of processes that involve those cations, and they're thought to be templates for zeolites. So if they truly act as templates and they enter into the pores and have to do with the size of the pores that get created, it kind of made sense to try larger and larger organic groups on the ammonium cation to make larger and larger pores in the zeolite. So in one sense, you can think of the objective may have been to try to make larger pores in zeolites. But what turned out to happen, and this was reported in a couple of papers, in 1992, there's a series of materials, these were made at Mobile at the time, where they used, instead of just being a tetra-alkyl ammonium cation, it actually is a surfactant. So the first example was cetyl trimethylammonium bromine. So it has a long tail, and the other groups are all alkyl groups. And the product of that reaction, it was a hydrothermal synthesis. So there have been a lot of variations on this, but the temperature is always above 100 degrees, done in an autoclave with dissolved silica as the source of the material at high pH. And it takes many days for this to happen, just like making a lot of zeolites. But the products have ordered pores, and the pores are larger than what you typically find in a zeolite. So they're on the order of 30 angstroms, as opposed to a large pore zeolite would be 10 to 14 angstroms. So there was a significant increase in the size of the pores that can be created in these kinds of materials, but the walls are amorphous, unlike a zeolite. So a zeolite is a crystalline material, but this process makes an amorphous silicate with ordered pores. And the process that's going on during their assembly is significantly different from what happens when you make zeolites, in the sense that it's very clear that the surfactants themselves, so I'm representing this little tail with the head as a surfactant, the surfactants assemble to make some kind of micellar structure in solution. And the idea is that the silica units, or you can use other transition metal precursors to do this, but if you're using silica, which is what I'm going to talk about, these little tetrahedra are supposed to represent individual monomers that link together to make the network. So there has to be some interaction between the head groups and the silica, and then as the silica network grows, if it's able to co-assemble with the surfactant, you can end up making this ordered porous structure, even though the walls themselves may just make some kind of disordered amorphous material. And the types of structures that can be made, now I'm showing the results of simulations. It's really not that important that they're simulations because people know that you can make these structures. But we're also doing some simulations to try to understand what conditions will favor different structures. But the kinds of porous structures that can be made, and what happens is that these things co-assemble with the surfactants first, and then at the end of the process, after the network has formed, the inorganic ceramic network forms, you remove the surfactant. And it can be removed usually by calcination or by extraction. But what's left behind are the pores, where the surfactant used to be. So one of the most common types of materials has this two-dimensional hexagonal close-packed array of pores. So that's what the open space is supposed to be, and then the gray area would be where the silica would be located. So that's the original kind of material was called MCM41 that has this kind of structure. But there are other structures that are possible. One is having a lamellar structure, so you have layers of surfactant and layers of silica initially. And if that's exactly the kind of structure you make, if you remove the surfactant, it will just collapse and you end up with silica. So it's not a porous material. But if you have little pillars that get created as part of, it can be a stable thermodynamic phase as this thing forms, it will hold open the little slit-like pores in between the layers of silica, and you end up with a porous material. So a pillared lamellar structure is another possibility. And a third possibility that's used a lot, and is maybe more important for catalysis ultimately, is a cubic structure. So in this kind of structure, I'm just showing where the pores would be actually in this kind of network, but it is a periodic structure, and you have actually three-dimensional connections between the pores. So this is just, this example that I'm showing here is called the gyroid phase sometimes, which is the mathematical description of the surface that divides the inorganic and organic parts of the original structure. But there are other types of cubic structures that can be made. And one of the simplest ways to think of it is if you have a bunch of spherical micelles and you just pack them together as tightly as possible, one possible way to do that is to make a cubic array of pores, and then the silica grows around it. Now what I'm going to be talking about today really is not relevant to catalysis itself, so I won't be testing catalysts. But I do want to emphasize that people are trying to use these materials as catalysts. And of course, part of the reason what I'll be talking about is that they have a very high surface area and very high pore volume. So an example of utilizing that is you can just take the silica type of materials that I'll be talking about today and impregnate them with a catalyst. And one example is for gas oil hydrocracking. Nickel and molybdenum were introduced by an incipient wetness impregnation technique and then calcined. And I'm not going to talk about the specific example, but there's a good review about the synthesis of these materials and their applications in catalysis from Jackie Ying and Angewandte Chemie, the international edition from 1999. So this is just one example. I'm going to show a few more examples later, but it's one thing that you can do is just take the silica and put something onto it, and it acts as a support. One of the advantages of this kind of materials, you can make a related material which is an aerogel that also has a very high surface area and is made by a similar technique. But the advantage of the surfactant templating is that you have more uniform walls, and they tend to be thicker than in aerogels. So that's better for a catalyst for the long-term stability of the material. And then people have done a lot of things with modifying the surface of the materials. So when you're finished making the material, you can imagine that you have a lot of silanol groups left over, OH groups on the surface, and it's hydrophilic. Those you can react with different silanes to, for instance, make organically functionalized materials. And obviously this wouldn't be useful for a lot of the high temperature, high pressure catalytic applications that probably a lot of you are thinking about, but for some of the lower temperature applications or liquid phase reactions, you can introduce very specific kinds of organic functionality into these pores and use them for some reactions. But it is possible to add, you can add transition metals also by introducing them as precursors along with the silica. And you can imagine, for instance, adding zirconium to your original solution, and in the walls you introduce zirconium. So you can do it either at the end to kind of functionalize the surface, or throughout the materials to introduce a transition metal. I don't expect very many people to be able to read this, actually. It's probably too small even for people near the front. But this is just a table taken from this review from Jackie Ying. And all that I'm trying to emphasize here is there have been a lot of studies introducing different metals into these types of materials. So aluminum, titanium, vanadium, all sorts of transition metals have been introduced. And the ultimate aim is to use them as catalysts. And again, this is too small for you to read, but it's another table. It's not even the complete table. This is another review from Chemistry of Materials, Sayari and Hamoudi. And some of the reactions that have been studied in these kinds of materials are oxidation reactions. And the kinds of things that have been introduced to do these oxidations are transition metals, enzymes, and different organometallic complexes have been introduced into the pores. So one example is a titanium-modified material where cyclohexene has been oxidized. There's a number of other substrates that have been tested for the oxidation. Also glycine, and let's see, there are other enzymes represented in this table, horseradish peroxidase, have been introduced. The advantage of using these materials for enzymes is that it stabilizes them, and stabilizes them both thermally and to the chemical environment of the liquid that surrounds the particles over what they would experience on their own. And there are also some organometallic complexes represented in this table. So I know you can't read that, of course, but there have been a lot of catalytic studies of these materials. And other kinds of reactions as well. So acid-catalyzed reactions, I don't want to spend too much time, base-catalyzed reactions, and some other types of enzymatic reactions, not just oxidation, have all been studied. And this SEM image that I've taken out of one of these papers just emphasizes one of the sort of maybe long-term sort of far-fetched applications, but you can use these materials as substrates for growing nanostructured materials that go beyond the ceramic structure that was originally there. So one example is you can do polymerization reactions from the porous material. So you put a catalyst into the porous material and then grow from it either polymers or nanotubes. And this is an example of kind of a carpet of nanotubes that was created by first making one of these ceramic materials, putting catalyst into it, and then growing the nanotubes. And you get a very regular array. So you can't really see that with SEM, but if you do TEM, and you can correlate the pore size of the original material and the carbon nanotube size. So those were just a few examples of catalytic applications, which I went through in kind of a sketchy way, but I just wanted to emphasize that you can use these materials as catalysts, of course, and as catalysts themselves. Now getting into the work that we're actually trying to do, what we're trying to do with this is kind of a new project. We've been doing it for about 9 months. And what people have done in making these materials is to try to use hydrocarbon surfactants, different types of surfactants to control the pore size and structure in the silica materials. So they've tried all sorts of hydrocarbon surfactants, cationic, non-ionic, and anionic surfactants. So that's basically all the varieties that you could try. And they've also changed the length of the surfactant tail. And they've tried different numbers of tails, single tails, double tails, different numbers of carbons in the alkyl chains in the tails. And they have shown that there is a good correlation between the structure of the surfactant and the structure of the pores that you get and the size of the pores. However, people have found that it's very difficult to get cationic surfactants to assemble with silica if the carbon length, this C10 means that there are 10 carbons in the tail of a surfactant. And that's kind of a disadvantage. That leaves a gap between the size of the pores that you can get in these surfactant templated materials. It's about 3 nanometers or so, 30 angstroms is the smallest pore that you can get. And zeolites. So in zeolites, the largest pore that you could possibly get is about 14 angstroms. So there's a gap in pore size. And so part of what we're trying to do, and we have other ideas, but we're trying to fill the gap between what you can get with hydrocarbon surfactants and what you can get in zeolites. And the way that we're trying to do that is by using fluorinated surfactants, and I'll get into why we're using fluorinated surfactants. So to get long-range order in these materials, some people have had success at using an 8-carbon surfactant that has 2 tails. So it just turns out that you can get better ordering and better assembly of the surfactants in the structure if they have 2 tails. And there's a mixture actually of double-tailed and single-tailed surfactants that allows you to do this. But there's really no prospect for being able to use smaller hydrocarbons, because once you get down to 6 carbons, they really don't assemble at all in solution. So what we're trying to do now is, and I'll show you some success, is using fluorinated surfactants as the templates to make ordered porous materials. Fluorocarbons are fundamentally different from hydrocarbon surfactants, and it's surprising maybe that nobody has tried to use them before. Part of the reason that fluorocarbons are so different is that there's a very strong bond between fluorine and carbon. It's stronger than the carbon-hydrogen bond in hydrocarbon surfactants. So that makes the interactions between these fluorinated tails and all solvents, both water and oil, very different than hydrocarbons. So they avoid both oil and water. So for instance, if you're trying to organically functionalize these materials, there's much less opportunity for that organic functionality to go into the pores. So remember that when the surfactant is removed, that's how the pores get created. So it'll keep the organic functionality away from the pore structure. So that's one advantage. There's also the possibility that we can use low surface tension solvents, like supercritical carbon dioxide, to extract these surfactants, which we wouldn't have been able to do with hydrocarbons. And the structure of these fluorocarbons is different than hydrocarbons. They tend to be stiffer. And this is just an illustration taken from a paper for just Teflon, for polytetrafluoroethylene, which is a fluorocarbon. You kind of get this helical structure because of the torsional potential of these chains, but the idea is that that makes them stiffer than hydrocarbons. And that causes them to assemble differently than the hydrocarbons would have under the same conditions and with a similar structure. So, for example, so what that means is that the surfactants assemble more easily, and they tend to make organized structures that have lower curvature. So what that means is that instead of making it maybe a spherical micelle, they will make an elongated micelle, a cylindrical micelle, because it has lower overall curvature. Or they might make planar structures instead of cylinders. So for instance, the surfactants that I'm going to be talking about have pyridinium head groups. That's just a cationic head group. And then if we have different chain lengths for the tails, one of the criteria for self-assembly that has to do with how good of a template these things are is just the critical micelle concentration. Now that doesn't tell you everything about what a surfactant does, but that's the concentration at which you start to form micelles. And the lower it is, the easier the assembly of that surfactant is. So, for example, if we have 12 carbons in a chain and we have a pyridinium head group, which is the one that I'm talking about, and it's a hydrocarbon, its critical micelle concentration is 15.5 millimolar at room temperature. If, on the other hand, we go down to an 8-carbon chain, the CMC goes up to 275 millimolar. So that means that it's a lot harder for this shorter chain surfactant to assemble. And on the other hand, if we look at a fluorinated version of that same surfactant, so this is this 8-carbon surfactant, this is the 8-carbon fluorinated surfactant. 2 of the carbons can be fluorinated to make it so that it's stable. But so it's as fluorinated as it can be and still remain stable. The critical micelle concentration now drops again to 16 or so at room temperature, which means that it will act more like the 12-carbon surfactant chain, hydrocarbon chain. So there should be easier assembly of this kind of surfactant. And there have been other studies of this kind of surfactant and how it behaves. And they do tend to make structures with lower curvature. So they make kind of worm-like micelles and elongated micelles instead of spherical micelles. And if we go to an even shorter fluorinated surfactant, the 6-carbon chain, it still has a critical micelle concentration of 170, so it's still lower than the 8-carbon hydrocarbon chain. So we suspect that we should be able to make smaller pore structures using these kinds of surfactants. So the surfactant that I'm going to be using, you don't really have to worry too much about how it was made, but this is the structure. So it's got a 6 fluorocarbon chain, and then it's got 2 hydrocarbon units just so that it's stable, and then a pyridinium head group. The pyridinium is not really important for our application. It was just the easiest thing to make, and it's cationic. And it behaves a lot like trimethylammonium if we compare it. And it's a chloride. And the way that we make our materials is very simple. We just take that surfactant and mix it with water and ammonium hydroxide. That we have to have this done at high pH. And we add to it, after letting it stir long enough to dissolve, we add to it tetraethoxysilane as a precursor. It will precipitate fairly quickly, but we still let it age for 24 hours, and that kind of perfects the order in the material. Filter it and let it dry, and extract the surfactant. And right now we're just extracting it with ethanol. It's kind of an ion exchange process, so we add hydrochloric acid, and it extracts the surfactant, and then we can dry it and do any further treatment. So the first thing that we wanted to check is whether, first of all, whether the surfactant gets incorporated when we first make the material, and whether it gets extracted when we try to do our extraction step. And so we did FTIR to see whether this is happening. So the first spectrum at the bottom is the surfactant itself, and it has a few characteristic bands, but the ones that we can actually use are here and here. This one, I think, has to do with the fluorine carbon asymmetric stretching. Doesn't matter really what it is. But when we first made our material, we just, these are the solid phase IR spectra mixed with KBR. Before we do the extraction, we see evidence that the surfactant is there. And one of the clearest indications is this peak, which wouldn't be present at all if we just had silica. And after we do the extraction, that band is gone. So we're sure that we were able to extract the silica, the surfactant at the end of this process. And it took it took 2 rounds of extraction to get it to that level. So then after having done that, we can start to characterize the pores in the materials. And the first way that we do that is by nitrogen adsorption. And these were outgassed for 4 hours at 120 degrees before doing that. So here's the raw data, the adsorption isotherm for the materials. The primary pore volume, which we actually get from the alpha plot, which I'll talk about in a second, is around 0.6 cubic centimeters per gram. And it's a type 4 isotherm, and it doesn't show any evidence for hysteresis. So we have this initial kind of well, it's not microporous, the initial monolayer and multilayer formation. But there's an inflection here, and it's maybe a little bit subtle. It's a lot more exaggerated when you have larger pores, but I'll show you why we think that that's real. So there's an inflection which indicates that there may be capillary condensation happening in mesopores. Now, we have to be careful in choosing a model for this system. We can't just use the BJH method or some of the standard methods that you might use to analyze nitrogen absorption data, because the pores are so small that the interactions between nitrogen and silica become very important. So one of the things that we do to analyze the surface area and, well, first of all, the surface area, is to use an alpha plot, which, if you're not familiar with them, this variable alpha, we use a standardized material, which is macroporous silica. And we kind of define it arbitrarily, but it's proportional to the amount of adsorption that occurs on that macroporous material at a given partial pressure. So we just take our partial pressure values and convert them into alpha, which just has to do with adsorption on a standard material. And so there are a few regimes that we can identify in this plot. And the first one, there should be a linear region at low partial pressures or low alpha values. And if that passes through the origin, that should indicate that there's no microporosity. I won't get into the details of that, but the slope of that initial region has to do with forming the initial layers of adsorbed nitrogen on the surface, and so it's proportional to the total surface area. And from that slope, we can measure the total surface area is around 970 square meters per gram. That's a little bit lower than what we would have gotten if we assumed, if we used the BET equation, but it's not that different. Then there's a positive deviation from that line that occurs eventually, and that's indicative of capillary condensation. So we're starting to get more adsorption than we would have had just from multi-layer adsorption on the surface. And we don't learn too much from where that happens, but eventually there's a second linear region after the capillary condensation is over, and at that point all the mesopores should be filled. So that has to do with external adsorption, and we can get an external surface area which is around 39 square meters per gram. So what that means is that we have fairly large particles, not a lot of external surface area, and most of the pores are mesoporous. And we have a fairly high surface area, is what we learned from that. Then to get information about the pore size distribution, we don't just use the BJH method because it's been shown to not be very accurate. I have a few references about this, but it turns out that you can get similar results if you use either a modified Kelvin equation to analyze the nitrogen absorption data, or a nonlinear density functional theory approach, which is a simulation method. But the important thing is that we have thought about this, and we've used a method that has been validated for these types of materials, for silica and nitrogen absorption, and we get a pore size distribution that's fairly narrow. So most of our pores are below 4 nanometers, and we have a peak pore size of about 2.57 nanometers, which is similar to what we could get with the hydrocarbon surfactant. So all that we've shown so far is that we have uniform pores, and we get similar pore size predicted with other methods that are just based on assuming that we have cylindrical pores. The VJH method predicts a smaller pore size, so that's the reason that we had to not use it. So we have a method that's consistent with all those methods. So the nitrogen absorption, all that really shows us is that we have uniform pores. To learn more about whether they're actually ordered or not, we use X-ray diffraction. And what we look for in the X-ray diffraction, now notice that the angles are fairly low. And the reason for that is that these pores, they're mesopores. So the order is on the order of, the order is happening on a length scale of several nanometers, not on the order of atoms. So we have to look at very low angles. And what we usually have to look for is more than one peak. So we don't have a lot of peaks and a lot of indexing that we can do. But if we see more than one peak, that's a really good indication for these types of materials. So we can actually see 3 peaks, and 2 of them are kind of weak, but that's not unusual in these materials. And we can index them to this kind of 2D hexagonal pore structure. And so this peak here is the 110 peak, and this is the 200 peak. And I'm showing you where the peaks would lie based on the D spacing from the 100 peak. So all of this means is that after extraction, we have a pore structure that's consistent with this hexagonal kind of pore structure. And we get a D spacing of 2.8 nanometers, which corresponds to A, the distance between the centers of pores, of 3.2 nanometers. So that's kind of consistent with the pore size that we got from nitrogen absorption, although it means that we have walls that are only about 0.7 nanometers thick. And that's relatively thin for these materials, but it's not out of the range that's been observed for other materials. And the final evidence that we have that these are they have the 2D hexagonal ordering is from TEM. And of course, TEM, it's easy to get kind of anecdotal evidence from just a few spots, but what we see when we take our materials and we just suspend them in acetone and put them on a grid, there are some regions that look like they have little stripes. And that might be a little bit difficult to see. I tried to increase the contrast on this image, but it just looks like stripes. And that would be consistent with a lamellar structure. So just seeing that alone doesn't tell us too much. But our interpretation of those stripes is that we have the 2D hexagonal structure. So we have cylindrical pores, but we're looking along the edge of the pores. So that would look like stripes because you're just kind of seeing the edges of an array of cylinders. If we zoom in kind of on this region of the image, you can see that there are little circles, which indicates that what we should be seeing is we're looking down the channels of this 2D hexagonal structure. And so we're actually looking into the channels. But you can imagine there's no orientation introducing these particles in any way. So it's very difficult. We have to spend a lot of time searching to actually find a region that's oriented like that in these images. But we happen to find one here. I think the X-ray diffraction and the nitrogen absorption are better indications, but the pore size that we see is consistent with the TEM images. And so it is around 2.5 to 3 nanometers in diameter is the pore size. And we also varied the surfactant to silica ratio in these materials And basically what we get is always very consistent results. We get a pore size distribution that's always very similar for a range of an order of magnitude of surfactant to silicon ratios and the 2D hexagonal structure. The only time that it starts to deviate from that is when we go to too high of a surfactant amount. And we're starting to think now that that's some kind of phase transition going on. And either it's just becoming disordered or it's becoming lamellar. But we don't have a whole lot of evidence for that yet. And I'm realizing this is running a little bit long. So I think actually I want to leave time for any questions. So I'm going to just skip to the end. So, I mean, that was the most important thing. We've also done some things with adding co-solvents to see how they go into the micelles and how they affect the pore structure. So just to conclude, I mean, what we've done right now is to use a fluorinated surfactant as a template for these ordered porous materials. And we've shown that we can extract it with acidic ethanol rather than using calcination to make the porous structure. We make pores that are about 2.6 nanometers in diameter, and it's consistent with X-ray diffraction and TEM. And I've done this solvent study that shows that the fluorinated core, we actually can use solvents to selectively go into the core of the micelles. And that may indicate that we can use supercritical carbon dioxide to do that also, but we haven't tried it yet. And we can make thin films also, which I didn't talk about. And I just want to acknowledge that Beth Dickey and Colleen Fraser, her student, helped us with setting up the characterization experiments, and Alan Dozier and Henry Francis at UK helped us with the equipment and let us use it. And it's supported by NSF and an RCTF fellowship for the student working on it. So thanks for your attention. I'm happy to answer your questions.
It's open for questions. Yes.
Obviously, you have Dr. zirconium into a simple structure. I'm wondering, can titanium be docked into the structure too? A second question is, what other transition metals can be docked into the structure? Like platinum, titanium, and platinum, or any other transition metal?
Yeah, that's a good question. So the question is, zirconia has been introduced into silica, so what other metals can be introduced? Titania definitely can be introduced, and it has been. There were a few examples. I would refer you to actually other people's reviews because I'm not really a catalysis expert. But this paper by Jackie Ying, well, then there's also this paper from Sayari and Hamoudi from Chemistry of Materials. So some of the entries on this table, yes, include titanium, modified materials. Some of the metals that have been incorporated, yes, a wide variety have been. So including aluminum, titanium, vanadium, boron, other just metals have also been. I know this is too small to read. This is also just taken from this review paper, so you can find that to learn more about what has been incorporated. Iron has been used, molybdenum, manganese. So yeah, there's a very wide variety can be incorporated. The main limitations, though, are in understanding how to do that and how to introduce the level of loading that you want in the materials. This table also includes a silica to dopant ratio, and these numbers, some of them are fairly small, like six silicons per aluminum, but some of them are very large, like you can only get on the order of 3,000 silicon per manganese, so it's a very low level of loading. And I think that's the challenge that people face, is that they don't really know how to introduce the transition metals exactly how they want to get good catalytic performance, especially.
The problem with the metal you said is too big to have you said the platinum or palladium, right? It's too big and you're going to distort the framework very much, so I don't think you can put them there. All these metals are comparable size with silicon. Other question?
And this pore structure helps thermal stability of this pore structure.
That's another good question. We haven't addressed that for our own materials yet, so that's an experiment that we need to do. I know that the hydrothermal stability of this type of material is an issue that still needs to be addressed. So, for instance, for the hydrocracking reactions, that's one of the main limitations, is that it's not as thermal as it needs to, as stable as it needs to be. But some of the materials can be made. You basically have to adjust the parameters so that the walls are thicker, and then they can be stable at 1,000 degrees for I don't know how long. But so it's possible to improve it, but it's not. It may not be what you need to be for every application.
There are reports, one from Mobile, Jackie King has another paper where they made aluminum MCM41 very stable for obvious applications. You have to be very careful also when you can calcine them to burn the template. You have to heat them up very slow. We use 2 or 3 degrees per minute. If you go 10 or 20, they're going to collapse.
Do you have any control on the length of this and how straight they are? To become spaghetti-like or they make strand, like a monolith?
Yeah. The pores, whether they're straight or not, and how long they can be. There is not much control over how long they are and how straight they are, and that is an issue because in the particles, even some of the images that we see in TEM, it's difficult to identify an oriented region because they're so small. So from the width of the X-ray diffraction peaks, the oriented domains seem to be about 13.2 nanometers in the particles that we make. So that's probably about the length of a straight section that we've got right now. But you can make thin films, in which case you can orient them for sure parallel to the surface of a film, which may not be what you want, but you can do that. We're trying to orient them perpendicular. We have some ideas about that, and then hopefully to have the pores go all the way through a film that's about a micron thick. But beyond that, I don't think anybody's shown tremendous lengths of pores that you can make with these materials.
The spherical ones, they can orient, just put on a water layer, and they're self-assembled into large hexagonal barrels, up to centimeter square here.
Well, I think you still have problems though, because of that just thermal fluctuations and bending just kind of spontaneously happens. But
can you comment on ideas you may want to pursue to preferentially orient the pores?
Well, it just has to do with the surface chemistry. So it's analogous to what people have done with block fill polymers. Basically, if you have a surface that is, I don't want to say neutral, I mean, it's ambivalent as far as what it prefers. So it doesn't have a preference for either end of the surfactant. It should make structures that are perpendicularly aligned. I think people have tried hydrophilic and hydrophobic surfaces as a contrast between those surfaces, but they should both induce the same alignment. They should be parallel to the surface. So that's our idea, is to try to make a substrate that is in between being hydrophilic and being hydrophobic, and that the substrate will help to align the structure.
Good luck. It's a nice problem.
Thanks. It is a hard problem.
Anybody else? Okay, let's try to close this paper. Thanks for speaking again.